So today we're going to talk about centripetal and centrifugal forces. In the last video, we learned about tangential and angular speed. I'll just remind you that tangential speed, symbolize it with a V, is equal to radial distance times angular speed, and that's symbolized with a lowercase omega. So we use this formula when we're talking about circular motion. So I'm going to give you a scenario to think about. Let's say that I have a can attached to a string and I'm spinning it over my head. So I'm spinning it in a circular motion. Let's say I'm spinning it counterclockwise, so something like this. Okay, so it's the center, and then this is the motion of the can. Alright, let's say that the string breaks right at this point. Okay, so what's the can going to do? Well, we know the can isn't going to continue to spin in a circular direction, right? Because the force, this tension right here between the string and the can is what was causing it to spin in a circular motion. So once that force is gone, what's going to happen to the can? Well, we know by Newton's first law that an object in motion will stay in motion. So it's going to continue on at a constant velocity going in this direction right here. Okay? So the direction of the velocity vector of the can is always tangent to this circle. Tangent meaning it only touches the circle at one point. So direction is tangent to the circle, that's why it's called tangential speed, and its velocity is constant because there's no other external force acting on the can at this point. So we know that the force of tension in the string is what was causing the can to move in a circular motion. When we have a force that causes something to move in a circular motion, it's called a centripetal force. In formal definition, I put it on this page right here, a force that causes an object to follow a circular path, it's a center-seeking force. So in our case, the tension in this string is a centripetal force. Centripetal forces can come in lots of different forms. It can come in the form of gravity or friction or tension, as long as it's causing something to move in a circular path. The centripetal force in this case, which is really just in the form of force of tension, is directed towards the center of the circle. So it's going in this direction. This is my force. We also know that acceleration is going to be in the same direction as the force vector, because remember that force is equal to mass times acceleration. Mass is a scalar, so acceleration has to be in the same direction as the force. So here's my acceleration vector in green. Alright. So in this case, I remember that the red vector was velocity. Okay. So what ends up happening is that I get circular motion because the velocity and the acceleration vectors combine, and it ends up looking something like that. That's how we get circular motion. So remember that the can wants to move in a constant direction in this direction, right? But a force is acting on the can and moving it in this direction, and you end up with something in the middle giving you this. So what happens when the string breaks? Well, when the string breaks, there's no centripetal force acting on the can, right? The can is no longer attached to the string which supplied the force of tension, so that's gone. And then we also know that the motion of the can goes off in this direction, right, at a constant speed in a straight line motion unless another force acts on the can, and we know that by Newton's first law. Okay, so this happens because there's no external force acting on the can, and that's why it continues to move in a straight line at a constant speed. So there is something called a centrifugal force, which is technically a fictitious force, but what it means is a center-fleeing force. So a force that makes an object move in a non-circular motion. This is a little bit confusing to grasp sometimes because centrifugal forces aren't legitimate forces, and that there is no action-reaction pair. If you recall, Newton's third law states that for every action, there is an equal and opposite reaction. So, for example, in centripetal forces, there is an action-reaction pair. The can feels a pull from the string, and then the can pushes back on the string as well. In centrifugal forces, there is no reaction pair. This might be easier understood with a probably example that you felt in real life. When you go around the bend and you're driving a car, right? So here I'll give you a little diagram. Okay, so here's your car. Your car wants to go straight, but you're turning the wheel, right? And what actually causes it to go in a circular motion is a force of friction that acts in this direction. This is like the velocity of the car here. This is force of friction. And then you end up with a circular path, like that. Okay, so there is a centripetal force on the car, and that's the force of friction. When you yourself are driving, there's no centripetal force acting on you. There's an absence of a centripetal force, which is called a centrifugal force. And if you recall, you usually kind of slam into the side of your car if you're driving fast enough when you turn. And that's because there is no centripetal force acting on you. So you, like your body in the car, doesn't want to move with the car in a circular path. And that's because you have an absence of a centripetal force, or you have a centrifugal force acting on you. So you feel the centrifugal force at your center of gravity. But it's not the centrifugal force that is pushing you into the side of the car. It's the absence of a centripetal force that would keep you moving with your car along that bend. So I've added the definition to centrifugal forces on the previous page. Centrifugal force is a center fleeing force, and notice that I put force in quotations because it's not a legitimate force. So this wraps up the video on centripetal and centrifugal forces. In the next video, we'll derive the equation for centripetal acceleration as well as centripetal force.